Good morning to you all. I think we are live. So this is our lecture 4 on control systems engineering. So just wait for more people to join here, and then we're going to start the discussion today. Today's topic of discussion is on transfer functions. All right. So you're already familiar with transfer functions, and here we're going to elaborate on that concept with slightly more rigorous details. As usual, if you have any query during the class, feel free to ask. I would actually be happy to answer your queries. Okay, just hold on. There is a problem with this. All right. I would just wait for 1 more minute, and then we're going to actually start the discussion. As usual, if you find something difficult to understand or if you want to ask any question, feel free to post them on the live chat. I'm monitoring that while I'm delivering the class here, and definitely I'll be answering your queries. So make sure to clear up your queries before we move on to the next lecture. And also please confirm that the audio quality and video quality are fine. You can see me properly. You can hear me properly. Please confirm that. Also, please confirm if everything is synchronized. Okay. Sometimes what happens is that the video lags and the audio just comes up in perfect time, but the video lags essentially. So there is a mismatch in synchronization. So if something like that happens during the discussion, also let me know. All right, so let's get started. Yeah, one of you are talking about a homework, right? And we're going to talk about the homework problem later. Okay, so don't worry about the homework problem. That appeared in your signals, that appeared in the signal flow graph, class on signal flow graph, right? Lecture 3. All right. So today we're going to talk about transfer functions. And transfer function, the idea of transfer functions is one of the fundamental, what should I say, mathematical concept, fundamental mathematical concept that helps us modeling transfer function, modeling systems, modeling physical systems, right? Okay, some of you are once again worried about the homeworks, and we're going to talk about the homework later, so don't worry. All right. So again, to discuss, transfer functions is one of the ways, one of the fundamental ways in which you can model, mathematically model a physical system. All right, just hold on. Right, so using transfer functions, we can actually easily model a special class of systems, dynamic systems. Of course, we're talking about dynamic systems, but a special class of dynamic systems. Now question is, what kind of dynamic systems can we model using the transfer function approach? That's the important question here. Okay. And soon we are going to realize that there is a very narrow specialized class of systems that we can actually model using the transfer function approach. Yeah, I understand that the messages approach late. I mean, there is some sort of a 30 seconds delay. Okay, when you type something in and it reaches me. All right. So yes, I do respond. You would see that I am responding. The responses are taking a certain amount of delay to reach you. Actually. Okay, so that's understandable. All right. So all the processing is involved. Anyway, so the idea is that if we have a system that conforms to these conditions, so there are certain conditions that are going to be imposed on the system, and you would realize that this kind of conditions are not extremely outrageous. Okay, in many situations we do actually have this kind of system that conform to these conditions that we are going to shortly impose on systems. And for systems that do not conform to these conditions, okay, we will see that we have methodologies through which we can actually convert or rather simplify the model into this kind of systems. Now, what kind of systems we're talking about? Of course, you have heard the nomenclature that, previously in your signals and systems classes. We are talking about a special class of systems which are called linear and time invariant systems. So, transfer function approach is applicable for linear time invariant systems. All right. So, if the system is non-linear, then the transfer function approach is not applicable. If the system is time variant, then the transfer function approach is not applicable for the system. All right. So LTI systems is the thing that we need to think about. So if I have an LTI system or a system that can be considered to be an LTI system, then it's good for us. We can actually work using the transfer function model. But there are certain caveats of the transfer function model which we shall come discussing later. Okay. So LTI, of course, in case you didn't know already, LTI stands for linear and time invariant system. Okay. So linear stands for, of course, a system that supports linearity. Okay, so if the input doubles, the output will also double. Okay, so that's linearity. So that's a part of linearity. It's called homogeneity, and also it supports superposition. So essentially, if x1 is the input and correspondingly y1 is the output, and if x2 is the input and y2 is the corresponding output, then any linear combination of these two will result into the same linear combination of the output. So that's the linearity property as a whole. Okay, if any system satisfies this sort of conditions, then the system is called a linear system. If not, then the system is called a non-linear system. But keep in mind, later on we are going to see that we can actually convert non-linear systems, or rather simplify the discussion on a non-linear system to become like a discussion on a linear system. Okay, with certain methodologies under certain conditions. Okay, so that is something we are going to discuss at a later point in time. Okay. Also, time invariance. The idea is that if xt is the input and yt is the output, time invariance tells me that if I shift the input by a certain amount of time, okay, it could be time advancing, it could be time delay. Okay, the output is going to shift by the same amount of time. The output will not change in its nature. It's only going to shift. Okay, the same amount of time. If that happens, then we call the system to be time invariant. Okay, so it doesn't matter when I apply the input. As long as I apply the same input, I will receive the same output. So that's the fundamental idea behind a time invariant system. Taken together, this sort of systems are called LTI systems, linear and time invariant systems. Okay, so we do only talk about linear and time invariant systems when we talk about transfer functions. All right. So if the system is non-linear, then you cannot calculate the transfer function of the system. If the system is time invariant, you cannot calculate the transfer function of the system. But also there are systems for which theoretically it is possible to construct the transfer functions, but the model often becomes so tedious and unworkable that we look for different methods. Something that we're going to discuss at a later class. Okay, For the moment, we are going to assume that it's a time invariant system and it has an impulse response of, let's say, let's call it GT. Okay. So GT is the impulse response of the time invariant system. Now, if you have followed along in our signals and systems classes, then you know it very well that for a linear and time invariant system, in short, for an LTI system, having the knowledge of the impulse response of the system is equivalent to having the physical system present with you, right? Mathematically speaking, right? So the idea is that the impulse response characterizes everything that is there to know about the physical system, right? So GT here is the impulse response. Just keep in mind, it's the impulse response. Now you might say that, okay, in signals and systems we used HT for representing impulse response. Now we are writing GT for representing impulse response. What's the deal? The deal is that this is a standard nomenclature. Whenever you are studying control systems, GT is considered to be the impulse response. So that's again a change in nomenclature, just a change in notation. Okay, nothing else. So GT and HT, they mean the same thing again, right? And say XT is the signal again in the time domain that denotes the input, okay, any arbitrary input, and YT denotes the output, any arbitrary output corresponding to this input. Okay, so when the system is excited with the input XT, the system generates an output YT. All right, and you know the relationship between the input and the output for this linear time invariant system is given by this. So if I know the impulse response, I can calculate the convolution of the impulse response with the input, okay, and then we can actually get the output. So this is, again, we proved this in our signals and systems classes, right? So by doing a convolution between the input and the impulse response of the system, we can actually calculate the output of the system to this particular input. So that is understood, right? And then while studying Fourier transforms, we realized that if we apply Fourier transform on both sides of this equation, essentially what we get is the Fourier transform of this YT. So we get the Fourier transform of this YT, and here we get the Fourier transform of this XT convolved with GT, and essentially we realize that this is equivalent to the Fourier transform of YT, which we can write as Y omega, assuming that the Fourier transform actually exists. And here the convolution of two signals, if I take the Fourier transform, say the Fourier transform of this signal individually is X omega, say the Fourier transform of this signal individually is G omega, then the Fourier transform of the convolution of XT and GT would be the product of the individual Fourier transforms. So this is going to be X omega times G omega. Okay, so that is something we also proved in our signals and systems classes. Okay, and from there we saw that G omega, which is supposedly the Fourier transform of the impulse response, is nothing but the ratio of the Fourier transform of the output to that of the input. So that is something we realized, we understood, right? So that's all with Fourier transform. Now Fourier transform comes with some severe disadvantages. So that will be understood when we actually talk about Laplace transforms. Okay, when I introduce Laplace transforms to you, we are going to discuss the fundamental shortcomings of Fourier transform. Okay, and that's how this is how the history goes. Okay, Joseph Fourier was a very brilliant young mathematician, and he invented Fourier analysis, right? But what he did, he wrote his research papers and he submitted his research papers to Laplace. Okay, Laplace, one of the biggest mathematicians back in the day. Laplace saw that the Fourier transform, the way Joseph Fourier developed it, was applicable to only a handful of functions. Okay, well, applicable to only a handful of functions. So he pretty much rejected Fourier's work. Laplace rejected Fourier's work. So of course Fourier was heartbroken, and what he did, he joined Napoleon's army. So he fought valiantly in Napoleon's army, and after coming back from the war, Napoleon was so pleased with Fourier that he actually gave Joseph Fourier, make Joseph Fourier the owner of a big estate. Okay, And that's how Joseph Fourier earned a lot of money. And with his own money, then later on, Joseph Fourier published his own research. Okay, Laplace didn't want to publish his research. So what Laplace did in the meantime, he got the research papers from Joseph Fourier. Laplace did not publish the papers from Joseph Fourier, saying that this was quite inferior, quite stupid work, because the functions, the things on which Fourier transform is applicable is a very narrow set of functions. So we cannot really work with these things. So Laplace invented a way in which you can perceivably apply the modified version of Fourier transform to perceivably in all sorts of functions. Okay, Fourier transform requires that three Dirichlet conditions must be satisfied. Okay, the three Dirichlet conditions must be satisfied. The signal must be bounded. First of all, the signal must have finite number of extremas and finite number of discontinuities. So these sort of things. Now many standard functions do not satisfy this sort of conditions. Okay, do not satisfy this sort of conditions. So Fourier transforms were not applicable to those sort of functions, right? So he modified the Fourier transform, and what he invented was a technique, sort of Fourier transform, that was applicable to a lot more functions. Okay, and he called it Laplace transform, of course. Okay, so Laplace transform was nothing but an extension of Fourier transform. All right, so that is how we are going to study Laplace transform in the discussion on Laplace transform, in our discussion on Laplace transforms. So just for the moment, remember this G omega is the ratio of the Fourier transform of the output of the system to that of the input of the system. This is not the transfer function. Okay, this is called the frequency response function. This G omega is known as the frequency response function. We discussed this in our signals and systems classes. And we realize that this is the function that determines if based on whatever input comes in, how much phase shift and how much amplitude modification will happen to in terms of the output. Okay, so the ratio of the output's magnitude to that of the input, and also the difference in the phase is determined by this. We actually once again derived this in our signals and systems classes, but that's not the thing that we want to discuss here. Okay, that is something we discussed in our signals and systems classes. This is not what we want to discuss here. Okay, so let's keep this aside. The idea is that instead of applying Fourier transform, if we apply Laplace transform on both sides here, okay, we end up getting exactly the same thing. As you might see, that we exactly end up getting the same thing. So here we're assuming that the Laplace transform of yt is ys, and we are assuming individually the Laplace transform of xt is xs, and the Laplace transform of gt is gs. And based on that assumption, and again we are going to later on prove this, you might already know that the Laplace transform of the convolution of two signals is equal to the product of their individual Laplace transforms. So this is going to be xs times gs. All right, and as such we can say that the impulse response, the gs here, gs, which is the Laplace transform of the impulse response, is nothing but ys by xs. Now there is another condition that should be appended with this. Okay, this is not the end. There should be another condition that should be appended with this, which I'm going to explain shortly. Okay, so that's how we define transfer functions. Okay, define transfer function. This is called the transfer function. This is sort of like transferring the input to the output. So if we convert the whole thing, this structure, take this and apply Laplace transform on the whole thing. So what happens is that this becomes xs, this becomes gs, and this becomes ys. So what happens is that ys, the output, becomes a product of the input and the impulse response. Of course, all of these are transformed. So essentially, applying Laplace transform here converts everything to something like a amplifier structure, gain structure. So this essentially becomes a gain. Okay, so this essentially becomes a gain. So whatever signal comes in, it multiplies with this, multiplies with the gain essentially, and that becomes the output. This is just like having an amplifier. So you have an amplifier, okay, an amplifier, say the amplifier has a gain of 5. So if the signal X comes in, the output would be 5X. So this is pretty similar to that, okay. So essentially this function GS kind of transfers the input to the output, right? So this is the function that transfers the input to become the to transform into the output. So it transfers the input to the output. So that's how the name came to be. So it's called the transfer function, a function that transfers the input to that of the output. Now, of course, all of these are happening after the Laplace transform has taken place. All right. So this way you can actually calculate the output, okay, like this. But then in order to calculate yt, you have to take an inverse Laplace transform on the whole thing. That way you're going to get yt. Okay. So again, just like applying Fourier transform and calculating these sort of things. Okay. So that is the fundamental idea here. All right. So in other words, you could say that the transfer function is the ratio of the output to that of the input for an LTI system. Of course, there is another condition which I'm going to mention shortly. Okay. But the better definition is that the transfer function of a system is the Laplace transform of the impulse response of the system. Okay. Transfer function of an LTI system is the Laplace transform of the impulse response of the system. All right. So that's again a very concrete definition. If you say that the transfer function of a system GS essentially is the Laplace transform of the impulse response of the system, then it's perfect. No issues. All right. Now try to understand that we are talking about dynamic systems, right? Dynamic systems. But the moment we say dynamic system, we understand. Again, this is something we discussed in our signals and systems classes. When we say dynamic systems, we are essentially talking about systems for which, in order to calculate the output at a present instance, we need the knowledge not only of the present input, but also the past inputs, right? So the present output depends on the present as well as possibly the past inputs as well, right? Now there is another type of dynamic systems for which you need the knowledge of the future inputs, but that's not possible in an analog case. Okay, so that way we are going to limit ourselves to only discussing systems that are causal in nature. So to be very specific, once again, we are only talking about causal systems here. Okay, in this course we shall be talking about causal systems only. Okay, systems for which to determine the present output you need the knowledge of the present input and the past inputs. Okay, present and past. Having the knowledge of these would be fine. You do not need the knowledge of the future. Okay, understood? So we are going to talk about causal dynamic systems, right? Now the idea is that if I have a continuous time causal dynamic system, then its mathematical relationship between the input and the output can be expressed through an ordinary differential equation. Okay, through an ordinary differential equation. So if we have a causal continuous time, which means it's an analog system, continuous time, causal, linear time invariant dynamic systems. All right. So if we have this kind of a system, see, I'm mentioning dynamic in brackets because what I want to mean is that static systems are also by definition causal systems. Okay, causal systems, and this kind of ideas do apply there as well. Just keep that in mind. So the idea is that they are expressed through differential equations, right? The mathematical relationship between the input and the output are often expressed through differential equations, right? So let's take a very simple example. And that way it will be more understandable, I hope. All right. So let's take a very simple example of a simple electrical circuit. Okay, simple electrical circuit. Say we have a signal source here. Okay, and that's a voltage source, and we have a resistor here. A very simple, once again, RC series circuit, and a capacitor here. All right, so this signal, let's call it xt. So the voltage signal, let's call it, okay, fine. Let's call the voltage signal Vt. It will be better for us to understand. And the resistor has a resistance of R, and say the capacitor has a capacitance of C. And so what we are doing right now, we are measuring the voltage across these two nodes, right? Measuring the voltage across the capacitor. So essentially, we are calling this voltage to be the output voltage. Let's call this VO, output voltage, which appears across the capacitor. So that's a very simple thing. I don't think anybody would get confused with this, right? Since we are all electrical engineers here, right? So it's not a very difficult thing to understand. All right. Let's say the current through this circuit, let's call it IT. Okay. So these are all functions of time. Okay. R and C are two parameters, and they are constants, and everything else are functions with respect to time, right? Both the input and the output, right? Now, of course, let's apply the Kirchhoff's voltage law, and so let's write the mesh equation. So we have only one mesh. Okay. So we have only one mesh. So there is a potential drop here. So for the convenience, let's put a minus sign here and let's put a plus sign here. Okay. So we have a potential gain here. So again, we are going from this direction to this direction, and using any standard technique, we know this is going to be minus Vt plus. Now, what is the potential drop across the resistor? That's going to be resistance times current. So that's the potential drop across the resistor. And now, what is the potential drop across the capacitor? I don't know. Okay, because I know that the current through a capacitor is defined like this. Okay. All right. So it's proportional to the rate of change of voltage across the capacitor. So I could write this as an integral equation, write this as an integration, but I want to avoid that. But of course, we know what is the potential drop across the capacitor. We know that we have defined it as V0t. Okay, so V0t has been defined as the potential drop across the capacitor, and then we actually are reaching the datum node here. Okay, reference node here. So this is the reference node. So you're reaching the reference node here. All right. So that way, we are ending with the equation. So one loop completes, and this is the mesh equation. Okay. So that's the case KVL equation, Kirchhoff's voltage law equation. All right. A very simple thing to understand. Now, for our convenience or keeping the nomenclature intact, let's call the input voltage to be xt, and the we are going to call that shortly. Okay. Now, think about this IT. Think about this IT. What is IT? IT is the current through the resistor, right? But this is also the current through the capacitor. Since this is also the current through the capacitor, we know that the current through the capacitor can be expressed like this. So this is the rate of change of voltage across the capacitor times capacitance, that gives you the current through the capacitor, and that's exactly equal to the current through the resistor, right? So that way we can actually replace this here. So that way the equation that we have becomes minus Vt plus R C times d V0 t dt plus V0 t equal to 0. That's now our simple differential equation. Okay, first order ordinary differential equation representing this system. So this is the dynamic system, right? And since this is the dynamic system, the representation is in terms of a differential equation of continuous time dynamic system, of course, analog, right? So now let's do a nomenclature change. So let's call Vt to be our input. Okay, so let's call it xt, the standard nomenclature. And since V0t is our output, let's just call it yt. So with this nomenclature change, we can actually write this as, so this is minus xt. Okay, x again representing the input, and this is R times C, and the derivative of yt, which is once again representing the output, plus again yt equal to 0. So that's the differential equation, right, representing the dynamics of this system. And as such, we can actually take the input to the right hand side and bring all the outputs to the left hand side. So we have RC times the derivative of the output voltage plus yt, and that's equal to xt, right? So that's again understandable. Now what we can do, we can apply Laplace transform on this. We could apply Fourier transforms on this as well, but unless xt and yt are well behaved signals, okay, we often cannot find the Fourier transform. Okay, we cannot find the Fourier transform. Okay, so let's apply Laplace transform. Again, we are going to explain rigorously the differences between the Laplace transform and Fourier transform. So apply Laplace transform. But before we apply Laplace transform, let's understand something very important. That assuming that, say for example, I have a signal, say ft, okay, and if the Laplace transform of ft, if it exists, is fs, then there are a few things you need to know. Again, we are going to prove all this in our respective classes. That the Laplace transform of the derivative of ft is fs minus f0 minus. Okay, so essentially the Laplace transform of the derivative of this derivative of the signal here is going to be s times fs. So s times the Laplace transform of the ft minus the initial condition on ft. So this is called the initial value of ft, right? Right, we actually have studied this in our mathematics classes, and again we are going to derive this in the proper context in our classes. All right, but if we ignore the initial conditions, so assuming zero initial conditions, okay, we can say that if I assume zero initial conditions, then that part is a zero. We can then say the Laplace transform of the derivative of ft will be sfs, and later on we are going to see that the Laplace transform of the second derivative of ft is going to be s square fs. Laplace transform of the nth derivative, so nth derivative of ft is s to the power n fs, assuming zero initial conditions. So with that assumption, these expressions might seem very familiar to you because they are very similar to the expressions that we derived with Fourier transforms as well. Again, just to recall, the Fourier transform of the derivative of this is j omega times x omega. Okay, the Fourier transform of the derivative of f would be, let's add xt, whatever. The Fourier transform of the derivative of this signal would be j omega times x omega. Fourier transform of the second derivative, again we derived these things in our signals and systems classes, so that is something we know. And just like that, the Fourier transform of the nth derivative of a signal is just this. So these are again pretty similar here. Okay, pretty similar, and we're going to derive these in due time, so don't worry about these. Just keep that in mind. So this is again a note you need to remember. So with that assumption, if we now consider that the Laplace transform of xt is xs, okay, and the Laplace transform of yt is ys, then we can say that this is equal to rc. So if I apply Laplace transform on the whole thing here, so let's apply Laplace transform on the whole thing. And if we assume that the Laplace transform of xt is xs and the Laplace transform of yt is ys, then the Laplace transform of the derivative, so RC are constant, Laplace transform of the derivative of yt is going to be s times ys, assuming zero initial conditions, okay, plus this is going to be ys, and this is going to be xs, okay. And from there we can actually calculate the ratio of the output to that of the input in the Laplace transform domain. So ratio of the Laplace transform of the output to that of the input. So this is, in this particular case, is going to become 1 by 1 plus, or rather 1 by src plus 1. Okay, but by definition we know that this is equal to the Laplace transform of the impulse response. Okay, the Laplace transform of the impulse response, which is also known as the transfer function of the system. So this is the transfer function of the system by definition. Okay, by definition. So we are again assuming zero initial conditions here. Unless that is satisfied, the idea of this application of Laplace transform and getting a transfer function out of this is not available to us, because if we don't have zero initial conditions, then we would have a spare term like RC minus RC y y0 minus, okay, something like that, and that term will be dangling around, right? So we won't be able to take the ratio of the Laplace transform of the output to that of the input. So this kind of idea will not exist. So going back to the previous discussion here, when we were saying that GT is the impulse response of the system, we were saying that the GT is the impulse response of the system under zero initial conditions. Okay, sorry, GT is the impulse response of the system under zero initial conditions, which means for an electrical circuit, as far as an electrical circuit is concerned, which means that there was no charge stored in the capacitors, there were no magnetic field stored in the inductors. Here, if I say something like RC times Y0 minus, what does that indicate? That indicates an initial term here corresponding to this. Okay, so that's something going to be the voltage across the capacitor when the system starts. Okay, so before I even have applied any voltage to the circuit, the capacitor, if the capacitor had some voltage already stored in it, okay, have some charge already stored in it, then it would already have some voltage across it, right? It will already have some voltage across it, and that is something we call the initial condition imposed on the system. All right, so to clarify this, make sure that we understand that GT is not only the impulse response, but the impulse response under zero initial conditions. Okay, so GT is the impulse response under zero initial conditions. Okay, so if I apply an impulse input to the system, and if everything was relaxed before that, okay, so if the capacitors were completely depleted, discharged, all the magnetic fields were depleted, okay, so all the inductors were discharged, under that condition, if we apply an impulse signal as the input, the output that I get would be GT, which is the impulse response of the system under zero initial conditions. And then if we take the Laplace transform of that, what we get is called the transfer function. So let's define the transfer function formally. So let's consider the formal definition of the transfer function. Formal definition of transfer functions. Okay, formal definition of transfer functions. All right, so this is going to be for a causal linear causal for a continuous time causal linear time invariant system. The Laplace transform of its impulse response under zero initial conditions is called the transfer function. of the system. Now this is conveniently for us is equal to the ratio of the Laplace transform of the output to that of the input. This is also sometimes written in some books. Okay, the transfer function is equal to, see, try to understand this, the transfer function is equal to the ratio of the Laplace transform of the output of the output to that of the input of the system. All right, so I hope you can read this and understand the definition here, right? So for a continuous time causal linear time invariant system, the Laplace transform its impulse response under zero initial conditions is called the transfer function of the system. Now this is conveniently equal to the ratio of the Laplace transform the output to that of the input of the system under zero initial conditions. Once again, so zero initial condition is once again there, under zero initial conditions. Okay, so again, once again, just to go back, okay, transfer function is defined as the Laplace transform of the impulse response under zero initial conditions. Conveniently, this is also equal to the ratio of the Laplace transform of the output to that of the input under zero initial conditions. Again, for continuous time causal linear time invariant systems. Okay, all right, so we're going to say that transfer functions GS are defined as the Laplace transform of GT. Again, GT stands for the impulse response of the system under zero initial conditions, and this is conveniently equal to the Laplace transform of the output to that of the input, all under zero initial conditions. All right, so that is something that is going to be equivalent here. All right, so any confusion here? All right, so that is going to be the formal definition of transfer functions for you. Just keep this in mind. Let me tell you honestly that in many exams and many interviews especially, if you ever say that you actually like control systems or you want to answer questions from control systems, inevitably, more likely than not, you are going to encounter this question. Okay, people are going to probably ask you this question. All right, you will see this question appearing. Okay, just hold on for a second. All right, understood? Okay, that is a very interesting question. We know, we have studied rigorously what Fourier transform does, right, to a signal. It especially if it essentially tells you all the constituent sinusoidal components inside the signal, right? So of course, a signal, a periodic signal or periodic signal, any signal, as long as it satisfies the Dirichlet conditions, it can be expressed as an infinite sum of different sinusoids, right? So, and that can be expressed using Fourier series or Fourier transform, depending on whether the signal is periodic or not. All right. Laplace transform is very similar. It also can work on many other signals. Okay, there are several signals for which you cannot even apply Fourier transform. Okay, the integral for the Fourier transform will not even converge. Okay, will not even converge. Let's take a very simple example. Like for example, let's take consider xt to be e to the power t. Let's take this very simple signal. Okay, and for this very simple signal, there exists no Fourier transform. The Fourier transform for this simple signal won't be there. You cannot calculate this. Okay, because it does not exist, as at least in terms of your standard functions, right? So it does not exist. So you understand that there are simple functions for which the Fourier transform does not exist. Okay, so you cannot really understand the sinusoidal components present in it. Okay, even if there are certain components present in it. All right. So Laplace transform actually alleviates this what should I say, restriction on Fourier transform. So when we discuss Laplace transform, we would actually start with the point of view of Laplace. Okay, Pierre Marcus de Laplace, actually when he receives Fourier's paper, this is the criticism he had. Okay, he saw the potential of Fourier's work, but he realized that the types of functions on which Fourier transform was applicable was very small. Okay, was a very small set of functions on which Fourier transforms are applicable. Okay, in reality, we often encounter many complicated signals, many different signals for which you cannot apply or cannot calculate Fourier transforms. Okay, so that's why Laplace transform is needed. So Laplace transforms are applicable. First of all, Laplace transforms are applicable to many other different types of signals for which the Fourier transforms are straight up not applicable. You cannot calculate the Fourier transforms. Okay, so the application area becomes much broader. That's one thing. There is another more interesting thing that I cannot discuss right now. Okay, we are going to talk about that when we discuss Laplace transforms. Okay, so and that's probably the more important thing than the broader applicability here. Okay, all right. So just to again mention this, of course I won't forget, this is part of the discussion here. Okay, so applying Fourier transform on a system, it can only give you, or for the most part, it can only give you the knowledge about what happens in the steady state for the system. Okay, so when the system has reached a steady state, what happens then? So that is something the Fourier transform, the application of Fourier transform on a system can actually give you information on. So often Fourier transforms are used in conjunction with steady state information. So if you want to figure out what happens to this system or what happens to the output in a steady state, okay, then we often apply Fourier transform. Just like in the idea of frequency response, just to go back, in the idea of frequency response, we realized that if we knew that the Fourier transform of the impulse response of this system was h omega, and I excited this system with a signal xt, which is a sinusoid, and again, the funny thing is that any signal can be expressed as sinusoids as long as it satisfies the Dirichlet conditions. And if this signal has something like a sinusoid of frequency omega plus some phase angle, then in the steady state, the output is going to be a times mod h omega. We actually derived this, right? This is going to be cosine. The frequency will remain the same, and the phase will get shifted by the phase angle of this complex quantity, which is again h omega, which is the Fourier transform of the impulse response. But this is in the steady state. Okay, so this very idea of frequency response is the steady state information. Okay, is a steady state information. So the idea is, once again, gives you information about the steady state of the system. So Fourier transforms are used in conjunction with steady state analysis of the systems. Okay, but Laplace transforms can give you more information about the system. Namely, Laplace transform, application of Laplace transform on a system can give you information on the transient states. Just to be very clear, okay, by applying Fourier transform, you can also get information on the transients. Okay, on the transients, but only in a limited scenario, only in a very limited scenario. Okay, you can understand the transients of a system. Okay, what happens between two successive steady states, that's called a transient. You can understand that using Fourier transforms as well, but the scenario will be very limited. Okay, the cases in which you can apply such a thing would be very limited. But Laplace transform is kind of a has much broader limitations. Okay, much broader. Okay, so it's applicable to much broader set of signals. So the limitations are much narrower, I would say. Okay, so Laplace transforms are often associated with transient analysis. Okay, and Fourier transforms are often associated with steady state analysis. But you can do both with both of them based on what scenario you're seeing. Okay, but Laplace transforms can be used to do steady state analysis as well. As I told you, Pierre Marcus Laplace invented Laplace transform as an extension of Fourier transform. So, in other words, whatever you can do using Fourier transforms, you can also do using Laplace transforms, but better. So, Laplace transform is kind of a better Fourier transform, if I want to say so, if I dare to say so. But that's the idea here. But why doesn't people use Laplace transform all the time? Yeah, that's a very good question. The answer is Fourier transforms are computationally easier. Okay, so if you want to write a computer program, you would rather go with Fourier transform than Laplace transform. Okay, because computationally speaking, Laplace transform is a much complicated process than calculating the Fourier transform. Yes, so that's the thing. All right, so that's again the basics here, right? So now let's generalize this. So generalization here. Okay. So what is the generalization? So when we discuss this for okay, once again, somehow I think you missed it. Laplace transforms can be used for steady state analysis as well as transient analysis. Transient. Okay. Transient states are states that happen between whatever happens to the system between two successive steady states. Okay, talking about the computational performance, yes, it is kind of what is related to modern era, right? So we often do many things computationally, and things that are computationally more efficient often takes the precedence over things that might be more elegant, more powerful, but also requires a lot of computation. Okay, so yes, since Fourier transforms are computationally more efficient than Laplace transforms correspondingly, so Laplace transforms are often used as a symbolic computation tool. Okay, often used as analysis tools. So not for really doing any actual practical stuff that we do with Fourier transforms all the time. Okay? Because we cannot do it computationally as efficiently as we can do with Fourier transforms. Just to make it clear, we can 100% use Laplace transform wherever we use Fourier transform. Okay, we can absolutely do that. But since it's computationally more inefficient, we do not do that. Okay? And oftentimes, what happens is that all physically available signals, they do satisfy the Dirichlet conditions. Okay, they do satisfy the Dirichlet conditions. So there is again won't be any question of applying Fourier transform, Laplace transform instead. Okay. So again, Laplace transform is kind of an analysis tool. Okay. All right. So generalization. The generalization is that if we are talking about system that has a differential equation which kind of looks like this. So again, we saw that the system here, this very simple system, was modeled using a differential equation. So let me just make it very clear. So this thing that we are having here, this equation is what we call a mathematical model of the system. Okay, so this is a mathematical, this does qualify as a mathematical model of the system. So this is the mathematical model of the system. Similarly, this is also a mathematical model of the system. This is also a mathematical model of the system. Okay, but what kind of mathematical model? They differ. Here, this is a differential equation based mathematical model. Okay, ordinary differential equation based mathematical model. And what kind of mathematical model is this one? This is the transfer function based mathematical model. Okay, so of course we can do the mathematical modeling in many different ways. So this is the mathematical model. So when we talk about transfer functions, we are actually doing mathematical modeling, transfer function based mathematical modeling. Okay, similarly here, if we write down the differential equation, we are doing differential equation based mathematical modeling. Okay, so these are all mathematical models. Now let's say the mathematical model for a system. Let's save this file. Just hold on. Let me save this file. All right, so let's say the mathematical model for the system is expressed, the differential equation based mathematical model is expressed with an nth order differential equation. Okay, again, xt is the input, yt is the output. Let's again draw this here. So say xt is the input and yt is the output, and again, this is a linear time invariant system. Linear time invariant system, which is causal, okay, and also with zero initial conditions. All these things must be satisfied. Now, let's say the differential equation that is describing this relationship between the output to that of the input, which is again called the differential equation based mathematical model of the system, is expressed like this. The nth derivative of y with respect to t. Again, I'm not writing yt, it is have to be assumed that this is a function of t. Okay. So these are again just derivatives. Okay. So this is nth derivative. Okay, this is n minus 1th derivative. So if this is the third derivative, this is the something like the second derivative, and so on. Okay. And so on. So this is and so on. These are called ellipses. Okay. So similarly, it will come down in the order, and this is going to be dy dt, and then something like, okay, and this is equal to something like the derivatives of input as well. So this is kind of a generalized model, generalized mathematical model for this kind of systems, linear time invariant systems, called the linear time invariant systems. And so on. All right. So that's again a differential equation that kind of represents all sorts of systems, right? Now, assuming zero initial conditions and applying Laplace transforms on this, and you notice something very important here. Okay, all these A's, okay, A1, A2, A3, A4 up to AN, and all these B1, B2, B3 up to BM, whatever, these have to be constants. Okay, these have to be constants in order for this system to be linear and time invariant. If any of these coefficients, like any of these A's or any of these B's, if these quantities are any of these quantities is dependent on time, if any of these things like B1, B2, B3, B0, B1, B2, B3, or A0, A1, A2, A3, whatever, if any of these coefficients are dependent on time, okay, is a function of time, then the system becomes time variant. Okay, if any of these functions are dependent on time, then the system becomes time variant. Okay, similarly, if any of these terms are dependent on x or y, okay, x or y, then the system becomes non-linear. Okay, so let's do again to mention these things properly. Okay, all these coefficients like a1, so all these a0, a1, so on up to an, and b0, b1, and so on up to bn must be constants for must be constant for if the system is linear and time invariant. Okay, so if the system is linear and time invariant, so they must be constant. Okay, so just to mention once again, if any of them are if any of them is a function of time t, then the system becomes time variant. Again, you studied this in your sequence and systems classes. Time variant systems are explicitly dependent on time. Okay, a very basic example would have something like this. For example, yt is equal to t xt. Now, for this kind of system, applying the same input at a different time would not give you the same output, right? Because t is explicitly there as a coefficient here. Okay, a function of t is explicitly there working as a coefficient here. Okay, similarly, if any of them is a function of x or y, then the system becomes non-linear. Okay, so in order for the system to be linear and time invariant, these must be constants. So they are not neither functions of time nor functions of the input and output variables. Okay, so now assuming zero initial conditions and assuming that all that conditions are satisfied, now we can apply the Laplace transform on this whole thing. Now applying Laplace transform on this equation, you know that the Laplace transform of yt essentially is ys. Laplace transform of derivative of yt is sys. Laplace transform of the nth derivative of yt is s to the power n ys, and so on. So if I apply the Laplace transform, so this becomes an s ys plus an minus 1, sorry, an s to the power n ys, an s to the power n minus 1 ys plus a1 s ys plus a0 ys, and this is equal to bm s to the power m xs plus bm minus 1 s to the power m minus 1 xs, and so on up to b1 s xs plus b0 xs. So that's again the Laplace transform version. Okay, and obviously the ratio of the output to that of the input, rather ratio of the output of the Laplace transform of the output to that of the input, again under zero initial conditions, assuming zero initial conditions, okay, is going to be, if we just take ys common out of this, factor out ys out of this entire equation on the left hand side and factor out xs from this entire equation from the right hand side, and then if we take these factors out, say essentially we are going to end up with something like this: an s to the power n plus an minus 1 s to the power n minus 1, and so on, a1 s plus a0, and here I have bm s to the power m plus bm minus 1 s to the power m minus 1, and so on, b1 s plus b0. All right, so that is once again going to be equal to the Laplace transform of the impulse response of the system under zero initial conditions. This is once again will be defined as the transfer function of the system. All right, so this is again a very generalized situation. Just to give you a very simple example, Just to give you a very simple example, let's say the differential equation based mathematical model of a system looks like this. All right, let's say the differential equation based mathematical model of a system looks like this. Now, assuming zero initial conditions per second and applying Laplace transform, we can say that this becomes, so this is the mathematical model once again, but differential equation based mathematical model. Okay, now assuming zero initial conditions and applying Laplace transforms, we have s 3 s cube ys plus 2 sys plus 5ys equal to 6xs plus 7. Okay, sorry, 7xs. And from that, we can say that the transfer function of the system, which is the ratio of the Laplace transform of the output to that of the input under zero initial conditions, is going to be 3s cube here plus 2s plus 5, and here I have 6s will be there. It's going to be 6s plus 7. All right, so that's going to be the transfer function of the system. Now let's go back and talk about why we even apply any transforms. Why can't we just deal with differential equations directly? Okay, that might be a question in your mind. Okay, why Fourier transform? Why Laplace transform? If I have the mathematical model as a differential equation based model, what is the problem? Because this is now a transfer function based model. What is the problem if we just had the differential equation based model? Is there any problem? Or why do we even need any transform? Why do we even need to apply Fourier transform on this, Laplace transform on this? Why can't we just deal with the differential equation based model? That's a very that would be a very interesting and important question to answer here. Okay. Now, to answer this question, let me ask you another question. What is more difficult to do, addition or multiplication, subtraction or division? If I give you, so for example, two numbers, for example, I give you one number and another number, and I ask you to divide, will it be easier for you to divide these two numbers? Of course, I'm talking about manual computation. Okay, even for a computer. Okay, will it be easier for you to divide these two numbers or subtract these two numbers? Which one is easier in terms of operation? Of course, division will be much more complicated than calculating the difference between two numbers, right? Subtraction is much more complicated than division. Similarly, multiplication is much more complicated than addition, right? Much more complicated than addition, right? Now let me ask you a simple question. What if you did not have to multiply two numbers? What if whenever I wanted you to calculate the product of two numbers, multiply two numbers, you could only end up subtracting numbers? You could only end up having to subtract two numbers and be happy with that. If that was the case, wouldn't that be a nice thing to do? Because doing division is much more complicated than doing subtraction. But there is a way in which you can actually do that. Now, of course, you are much younger, and you might ask your parents, and they might have used this. Back in their days, people used to have something called logarithm tables, log tables in short. Okay, what would log tables essentially do is, for example, in your exams. Okay, nowadays you can actually bring your calculator, right, to do computations in your exam. But imagine in your exam you wanted to calculate the ratio, the quotient of these two quantities, divide to these quantities. Okay. Okay, how would you divide these two numbers? Of course, you can do a long division, but it would take a long time. So what can you do? You can instead apply the concept of logarithm. So you would have a log table, and based on the log table, you would actually calculate the logarithm of these two numbers. Now, logarithm is a very interesting concept here. Okay, the log of the ratio of two numbers is the difference of their individual logarithms. That's going to be log of this minus log of that. So using the log table, you would find out these two numbers. Okay. So look up. So you would be looking up at log tables, and you would find out these two numbers. Let's say this is going to be x and this is going to be y. So you will find them from the log table, and you subtract them. You subtract them, right? You subtract them. So you end up with some other result. Let's call this z. Okay. The result of this subtraction. So z. Now what is z representing? Z representing the logarithm of a certain number. Let's say that this number, what is the result is q. Then z is essentially representing the log of q. Z is representing the log of q, right? Right? So that's understandable, I guess. And then alongside the log table, you would have another table called the anti-log table. What is the anti-log? The anti-log is just the opposite thing, because if the log of q is z, then q is 10 to the power z. Okay. So the anti-log table would give you that value. So you would have the value z, and from that anti-log table, you would end up getting q. But what is q? Q is this very quotient that you sought to figure out. So using a log table, without actually ever calculating the division of two numbers, you can divide two numbers. Okay. You can divide two numbers. So that's the idea. So what did the logarithm do? The logarithm converted the division into a subtraction. The logarithm converted the multiplication into an addition. Doing addition is much better than doing multiplication. Doing division, doing subtraction is much better than doing division. A very similar thing is done by the transforms, the Fourier transform and the Laplace transform. Okay. You see, let's go back to the very system here. The mathematical model that we had was a differential equation, right? This was a differential equation. But the moment we applied a Laplace transform, it is no longer a differential equation. Application of the Laplace transform turned it into an algebraic equation. This is an algebraic equation, right? Similarly, look at this. So this is an nth order differential equation. Now, by application of Laplace transform, this got converted into an algebraic equation. See, this is an algebraic equation. This is no longer a differential equation. Now, I might ask you, what is easier to do, solving a differential equation or solving an algebraic equation? The answer is going to be obviously yes, solving an algebraic equation, right? Solving an algebraic equation is much easier than solving a differential equation. That's the idea. Laplace transforms as well as Fourier transforms, they convert differential equations into algebraic equations, and solving algebraic equations are much easier than solving differential equations. So this is one of the primary reasons why we do not just directly deal with differential equation models of the systems. Instead, we convert it to a corresponding transfer function or frequency response model. Okay, and then work with that, because that's an algebraic model. Okay, not a differential equation based model. So transfer function models are inherently algebraic models. See, this is an algebraic quantity. This is a polynomial in the numerator, also a polynomial in the denominator. So this is an algebraic quantity, right? So this is an algebraic form. So the transforms actually convert differential equations into algebraic equations, and that's how they got their names. Okay, that's how they are called transforms. Okay, the original names. All right. So I think that actually clears up a very important notion here. So get rid of this, not needed. All right, so let's talk about some a few more important concepts regarding this, and then we're going to close this discussion. Okay, so this is the standardized transfer function here. Okay, So in general, you have this sort of a transfer function, right? So this is a polynomial in the numerator. This is another polynomial in the denominator, right? Polynomial in the numerator, polynomial in the denominator. The idea is that if you have a polynomial, then the polynomials can be factorized, right? Any polynomial can be factorized. As a matter of fact, if you consider complex factors, and these are all complex numbers, okay? If you consider complex numbers, then any order polynomial will have n number of factors, essentially, okay? N number of factors. So we can actually convert this and factorize this. So let's see an example, rather, I would say. Let's see an example. Let's say that transfer function looks like this. Say 2s plus 5 divided by, say, s square plus 3s plus 2. Then of course we can factorize everything. We can say, okay, this is going to be 2 by 2 times s plus 5 by 2, and here it is going to be s plus 1 times s plus 2. We can factorize polynomials like that, right? In complex numbers as well. So let's say if we factorize this, and of course, say for example, if we had a factor here, so for example 5 here, or maybe 7 here, we could actually bring this factor up. We can divide everything. So we can divide everything with this factor here, right? We can divide this factor here, and we can take care of everything accordingly. Okay, this is how we can manipulate polynomials very easily. Not a problem. So idea is that we can actually convert this into a factorized form. And if we convert it into a factorized form, we would end up with factors. Okay, so n number of factors in the denominator and m number of factors in the numerator polynomial, of course. So this is going to become something like s minus. So I'm just writing minus, you could write plus, whatever. S minus P0, sorry, P1, S minus P2, S minus P3, and so on. So n number of factors, because it's an nth order polynomial here, n s minus Pn. And the numerator also, we are going to have m number of factors. So this is going to be s minus, say for example, z1, s minus z2, s minus z3, and so on, s minus zm. Of course, I have to take care of this highest coefficient. So let's divide everything, and we are going to end up with a constant term here. So that's a constant. That's again a factorized form of the transfer function. This is again simple algebra, right? Understandable. All right. Now look at this example, as I told you already. Now in this example, what if I choose s to be equal to minus 5 by 2? What if I put s to be equal to minus 5 by 2? What if I put that s equal to minus 5 by 2? What's going to happen? So if I put s equal to minus 5 by 2, I would see that this is becoming 0, because s equal to minus 5 by 2, putting it here gives you a 0 here, and that's how the transfer function becomes 0, right? Becomes 0. So what we say is that s equal to minus 5 by 2 is a 0 of the transfer function, because if you put s equal to minus 5 by 2, the transfer function will become equal to 0. Okay, so that's why this particular value here is called a 0 of the transfer function. Okay, it's a 0 of the transfer function because putting this value in the transfer function in s, okay, replacing s with this value, okay, gives you a 0. Okay, so we call that a 0 of the transfer function. So again, look at this. If I put s equal to z1, if I put s equal to z2, if I put s equal to z3, or anything up to zm, the transfer function becomes 0, right? Gs becomes 0. The transfer function becomes 0. So all these values, s1, s equal to z1, s equal to z2, s equal to z3, and so on up to s equal to zm, are called the zeros of the transfer function. Zeros of the transfer functions. So when I put these values in place of s, the transfer function becomes 0. Notice that the denominator does not become 0. Okay? Only the factor in the numerator actually becomes 0. Okay? So these are called the zeros of the transfer function. Now if I ask you this question, but in a slightly other way, let's say I put s equal to -1 in this. If I put s equal to -1, what happens? I would wait for a minute and expect you to answer this question. All right, it seems only a few of you are answering actively. All right, infinity, right? So yes, so you got it correct. So if I put s equal to -1, then this here becomes 0. This factor in the denominator becomes 0. So I get an infinity, right? So anytime that happens, we call it a pole of the transfer function. Now what is a pole? Now it's called a pole, this name actually came from a very interesting thing in complex analysis. Okay, essentially maybe, okay, someone is saying we have to do partial fractions to solve this. Yes, and we are going to need partial fractions in many of the situations, and I'm going to teach you everything that you would need, both computationally through Python programming and also analytically by hand. Okay, so don't worry about all the mathematical requisites you need. All right, so s equal to -1. If I put s equal to -1, I get an infinity for GS, right? If I similarly put s equal to -2, I once again get an infinity. So for whatever values I get an infinity for the transfer function, we call them poles of the transfer function. So let me just copy this and paste this here. So we know if I put s equal to p1, s equal to p2, p3 up to pn, any of these values, then this becomes infinity. Again, we are still on the nomenclature phase. We are still discussing the nomenclature. No, well done. All right. So now we're still again in the nomenclature phase here. All right. So all right. So this is going to be P1, P2, P3, and Pn. Up to all these factors, say if I put s equal to P1, P2, P3 up to Pn, so the transfer function becomes infinity. So these are called the poles of the transfer function. Poles of the transfer function. Okay. These are the poles of the transfer function essentially. So again, the name pole essentially came from a complex analysis idea. So imagine you are walking in a field. So complex numbers can be described as 2D in the Cartesian plane, right? So this is like the x coordinate, which is the real part of the complex number, and this is the imaginary part of the complex number. So this is like a big field here. Okay, and you are walking along the field and you see an infinity. What would the infinity appear like? The infinity would probably appear like a long goalpost, sort of, right? You have been in playing fields, you have seen goalposts. That's like a pole, long stick in the middle of the ground, something like that. Imagine that kind of a simile here. Okay, so that's how we call them poles of the transfer function. Okay, and here this k here, okay, that k is called the gain of the transfer function. This k is the gain of the transfer function. Okay, k is the gain of the transfer function. So just keep these names in mind. All right. So this sort of form where we actually factorize everything and express the transfer function in this way, okay, where I have we can see the poles, we can see the zeros, and we can also see the gain. It is known as the pole zero gain form of a transfer function. So this sort of form where we actually represent everything in terms of poles, zeros, and gains is called a pole zero gain form. Okay, so this form of transfer function is known as the pole zero gain form of transfer functions. So transfer functions are again representable in many different ways. So this is called the polynomial form of a transfer function when we express them as polynomials. So this is a polynomial form. And this is the pole zero gain form. Now poles are represented with P, okay, and zeros are represented with Z, and gains are represented with K. So sometimes this is called, okay, just zeros come first. The name is kind of like this: zero pole gain form. So zero pole gain, not pole zero gain exactly. So this is sometimes in short called ZPK form. Okay. So zero pole gain form. K stands for gain here. Okay. So that's the ZPK form of a transfer function. All right. So just keep that in mind. Now I told you that this system, of course, whatever description, mathematical description we are dealing with, came from a differential equation, right? Came from a differential equation. But my question to you right now is this: what is the order of this differential equation? What is the order of this differential equation? Can anybody tell me? Not sorry, this differential equation. What is the order of this differential equation? So can anybody tell me the order of this differential equation? Okay, everybody is agreeing that the order is n. Anybody else might want to say? Anything else? Okay, all of them are agreeing on n. Okay. Okay, why not m? Why not m? Question is, why not m is the order of the differential equation? Why is it that n is the order of the differential equation, not m? Of course, just to define what is the order of a differential equation, highest order derivative present in the differential equation. So 10th order derivative is present in the differential equation, so it becomes a. Okay, so one of them has got a very interesting answer. So if we think about with respect to y, then the order is n, and think about with respect to x, the order is n. So both m and n are actually correct answers. Okay, both m and n are actually correct answers. But to be very exact here in terms of mathematics, we are going to assume in our throughout our classes, we are going to assume that n is at least greater than or equal to m. So in that context, we can say that the order of the differential equation has to be n, right? Since n is greater than or equal to m, it could be m if they are equal. Okay, in that case, this is also will be equal to n. So if, so for example, if this is a third order differential equation here, also a third order differential equation here, in that case, m and n are equal. But this is again another standard assumption in our consideration here. N is greater than or equal to m. Okay. So with that being said, this is an nth order polynomial, this is an mth order polynomial. Okay, and number of zeros will be at most equal to the number of poles. Okay, got this? Because you see the differential equation, the order here was equal to n, the order here was equal to n. So essentially here I had up to s to the power n, so it was an nth order polynomial, and here it was an mth order polynomial. So here the order of the polynomial is m, here the order of the polynomial is n. So if I factorize this, I would get n number of factors. So I have n number of poles. And if I factorize this, I get m number of factors. So I have m number of zeros. But since n is greater than or equal to m, since n is greater than or equal to m, so I have at least the same number of poles as zeros. Okay, if not more poles than zeros. Okay, so often you would encounter situations that where number of poles would be larger than number of zeros. Okay, they can at most be equal, but number of zeros can never be more than number of poles, at least in our consideration here. Okay, so this kind of transfer functions where this condition is satisfied. Okay, so we are, let's put that here. We are saying that n is greater than or equal to m. This assumption is called a rational transfer function assumption. Rational transfer function assumption. So we are only going to deal with rational transfer functions. So I already gave you way too many conditions, and still fortunately you will see that many physical systems can be actually expressed in terms of rational transfer functions very actually easily. We're going to do the modeling part from our next class. So please let me know if you understood whatever we discussed in today's class, or if there is anything that you might have found difficult to understand in this class. Of course, regarding the exercise problem that we gave you yesterday, in the last class, we are going to arrange additional classes for dealing with those. Okay, additional doubt clearing classes using Google Meet. You'll get the new information in that. So with that being said, if you have any query regarding what we have discussed today, please feel free to ask. Just to once again mention, this transfer function has m number of zeros. This transfer function has n number of poles. Okay, so m number of zeros, n number of poles. Okay, and there is an idea of the order of the system. I'm going to talk about that in the later class. Just keep in mind, the number of poles of the system is also known as the order of the system. So this is an nth order system because there are n number of poles. This is a third order system because this has 3 number of poles, right? So this is a third order polynomial. So this is a third order system. Okay. Okay. Similarly, this is a first order system because this is the first order polynomial in terms of S. So this is the first order system. So the order of the system is defined by the number of poles present in the system. Why is it so? I'm going to explain in the next class, in a future class. Okay, just keep in mind the order of the system is defined as the number of poles. Okay. All right. So anything else you might want to ask? I think it's all clear. So thank you very much. I will actually end the discussion here. I will see you in tomorrow's lab.